So we left off right here speaking about the hemoglobin-oxygen dissociation curve, and we were looking at how hemoglobin can behave differently at different partial pressures, and that can influence the way that it binds oxygen, the way that it wants to attach or attract that oxygen. And so just to review this here, we spoke about things that shift our curve to the right. And shifting our curve to the right means that, one, it's going to require a higher partial pressure to fully saturate hemoglobin, right? Higher partial pressures would be required to get oxygen onto hemoglobin, but then lower partial pressures would be required to remove that oxygen from hemoglobin, right? It's going to be harder to load it on, but easier to load it off or to remove it into those tissues. And so thinking about right shift scenarios, these are advantageous in times of metabolic activity increase, exercise, increased fight or flight response based upon that relationship. If we think about exercising, your muscles are generating lots of heat. And so those specific muscles are going to load or offload, oxygen from that hemoglobin a little bit easier as a way to oxygenate those tissues. And so it's going to be advantageous in those types of scenarios to have your curve shifting to the right. In the opposite scenario, we think about left shift states. This is where there's decreased body temperature. We talked about decreased altitudes where there are higher partial pressures, decreased metabolic activity. And in these types of scenarios, a lower partial pressure is needed to fully saturate hemoglobin, but then a higher partial pressure is needed to unsaturate hemoglobin. So it's going to require a higher partial pressure to take that oxygen off of hemoglobin, okay? Because there's a higher attraction, higher affinity of hemoglobin for that oxygen. And again, these are states where there's not increased metabolic activity, and that would be advantageous. You want that hemoglobin to tightly bind onto oxygen because it's not as easy, it's not needed as much in these types of scenarios, okay? All right, now what we're going to speak about, and just to kind of, again, talk about what this all is, this is cooperative binding. So this is basically saying that hemoglobin behaves differently at different partial pressures, depending on some of these states, body temperature, metabolic activity, and we'll talk about some other things that influence how hemoglobin behaves and how this curve can shift to the left and right based upon some other factors going forward. So this brings us to speaking about the Bohr effect. And the Bohr effect is another influence of how hemoglobin behaves, but this is under the influence of lower pH. And when we say lower pH, you want to be thinking about higher acidity, right? Higher amounts of acid that are produced in these tissues. And so that increases the way that oxygen unloads from hemoglobin. And so this is going to shift our curve to the right. This is evident in active tissues where the tissues are producing more acid, especially muscle tissues, more lactic acid. We're going to see a lower pH in these types of tissues, meaning more acid. That is going to shift our curve to the right, which again is making it harder to load that oxygen on, but easier to load that oxygen off and into the tissues. And so that's another thing that can affect or influence the way that hemoglobin behaves, that pH or that acidity. So let's illustrate that here, the Bohr effect. Okay, so again, we're comparing, the percent saturation of hemoglobin with oxygen and comparing that to the partial pressure of oxygen. Right, so partial pressure of oxygen here versus the percent of hemoglobin, oxygen saturation. Okay, and so max would be at 100. Remember, 100 means that there are 4 oxygens bound to hemoglobin. Let's first start by describing what the Bohr effect is. So the Bohr effect is the influence of hemoglobin, the way that it wants to bind oxygen in the presence of acidity or lower pH. So we have hemoglobin plus oxygen. This is deoxyhemoglobin. That can be converted to oxyhemoglobin, which is, and this is reversible, excuse me, which is hemoglobin, which has oxygen bound, and then we have some hydrogen ions being released, right? So here's oxyhemoglobin versus deoxyhemoglobin. Okay, and based upon what we described before, that law of mass action, so the law of mass action said that if we had more of our products, we drive the reaction to the left. If we have more of our reactant, we drive the reaction to the right. Okay, so in this scenario, if we have more acid, more of our product, we're going to drive the reaction to the left. Okay, so increased acidity or increased hydrogen ions, which is synonymous with lower pH, drives our reaction to the left. In other words, oxygen dissociates more easily. Okay, in other words, our curve is shifted to the right, so right shift. Okay, so a couple different ways to express what's happening here, as hemoglobin and oxygen are no longer attracted or tightly affiliated to each other. And so it's going to, oxygen is going to dissociate more easily or more readily as we drive the reaction towards the production of deoxyhemoglobin, okay, by the presence of excess acidity. So again, just drawing our standard curve here, this is what our sigmoidal curve looked like. Right, and then if we shift it to the right, we are looking at more acid or lower pH. So here's our right shift. So lower pH, in other words, more hydrogen ions causes a right shift. And then we can also think about lactic acid production, specifically in our muscles. Right? Or in general, just increased metabolic activity in tissues.
I have a quick question.
Yep, sure.
So in the top, it says increased hydrogen and lower pH drives a reaction to the left. But then in the diagram, you have it going to the right.
So the curve is, that's a good question. Thank you for bringing that up. The curve is shifted to the right, but the reaction is being driven to the left here. So they're not necessarily related, but I'm glad you pointed that out because that may confuse other people as well. But what we're saying when we shift our curve to the right, this is talking about how easily hemoglobin and oxygen are attracted to each other. And so a right shift just means that we need higher partial pressures to fully saturate hemoglobin, right, to bind all four of those oxygens on, because there's not that attraction that we see in a typical scenario or even a left shift scenario. In terms of this being shifted to the left here, what we're meaning is that there's more production of deoxyhemoglobin. So the left shift of the reaction, and I don't want to say shift, but the left, driving the reaction to the left here is the same thing as shifting our curve to the right. All right, I hope that makes sense. So they're not like the same idea. We could have reversed this reaction. If we had deoxyhemoglobin on the right and oxyhemoglobin on the left, then we would drive the reaction to the right. but it's not the same thing as shifting our curve in either direction, if that makes sense. All right. But that's a good point to raise because that may be a confusing point for others. Let's look at what happens with a left shift. Yes, excellent. So I'm seeing in the chat a question, does the right shift mean what would happen in exercise? Yes, it does. So exercise where muscles are under, more metabolic demand, they have more heat being generated. All of that is synonymous with increased metabolic activity, with a right shift of our curve, with hemoglobin and oxygen not being as attracted or affiliated to each other, such that oxygen can easily dissociate off into those tissues, which is an advantageous thing to have in those types of scenarios. Okay. And then just reviewing here what happens with our left shift, which is the opposite. Our left shift would happen if we had a higher pH. In other words, less acidity, right? Less hydrogen ions. And that would cause a left shift. Okay. Right, I hope that's clear. So we've got a right shift if we have more acidity, more heat being generated from those tissues. But if we're thinking specifically about the Bohr effect, the Bohr effect is the only looking at the influence of acidity and hydrogen ions on the way that hemoglobin wants to bind to oxygen, okay? But other things can shift our curve to the right as well, right? But in general, we think about increased metabolic activity, which does lead to increased acid production, okay? All right, so that's one thing that can also shift our curve, looking at it at the specific effect, the Bohr effect. Another thing that can influence our curve or can influence the way that hemoglobin wants to bind to oxygen is carbon dioxide. So this brings us to looking at the Carb-Amino effect. And so carbon dioxide is going to react with hemoglobin to form carb-amino hemoglobin. So we can bind that carbon dioxide onto hemoglobin to a lesser extent. We talked about that, and that would produce carb-amino hemoglobin. And hemoglobin has this weird behavior. Whenever there's lots of CO2 around, it doesn't want to bind to oxygen. And kind of the easiest scenario that I think about is hemoglobin acting like a guy in the middle of a three-way relationship. Whenever there's lots of CO2 around, it doesn't like oxygen. And whenever there's a little bit of CO2 around, it somehow loves or is attracted to oxygen. Okay, so it's going to have a lower affinity for oxygen than hemoglobin, such that increased CO2, which is a byproduct of increased metabolic activity, causes that right shift where oxygen unloads more easily into the tissues and is not as attracted to hemoglobin as we have in normal scenarios. Okay, so let's illustrate that here as well. This is called the Carb-Amino effect. And let's just illustrate that again for clarity here. So the Carb-Amino effect. And so we're thinking about hemoglobin plus CO2, and we have our reaction that is being catalyzed towards carb-amino hemoglobin, right? When that hemoglobin binds some CO2. So here we have plain old hemoglobin, and then here we have carb-amino hemoglobin, right? Yes, so someone's asking if HbCO2 stands for carb-amino hemoglobin. Yes, it does. And again, thinking about our law of mass action, right? We're thinking about states where there is increased CO2, which is also happening as a byproduct of increased metabolic activity. That is going to drive our reaction to the left. All right, and that means oxygen dissociates more easily. In other words, our curve is going to shift to the right. And I'm going to actually put here, instead of just right shift, I'm going to put right shift of the hemoglobin oxygen dissociation curve. Just so that we understand it has nothing to do with this left or right. Okay, I could have reversed the direction of these two products. A left shift, driving the reaction to the left just means that we're producing more hemoglobin, right? We're taking that carbon dioxide off and we're producing more hemoglobin. All right. So essentially, this is another thing that can cause our curves to shift to the right. This is where hemoglobin and oxygen are not tightly associated. And as I mentioned earlier, this is seen when there's a lot of CO2 around. Hemoglobin does not want to bind to oxygen in the presence of a lot of carbon dioxide. Okay, so just reiterating this here with our graph, we've got the percent saturation, hemoglobin, oxygen saturation. We're comparing that to the partial pressure of oxygen here. All right, and so we think about our standard curve in the center here. We think about our right shift, which is going to be in the presence of more carbon dioxide. So increased carbon dioxide causes a right shift. And we can also think about increased metabolic activity here as well. Right? Tissues that are respiring more, are consuming more oxygen and producing more CO2. And so it's advantageous to have oxygen easily dissociate if the tissues are producing more CO2 so that more oxygen can move into those tissues and deoxygenate them. All right. And then the opposite scenario here. Oops, I didn't even draw the curve. All right, so here's our right shifting curve. And then on the opposite end, we have our left shift to the curve, okay? And so here we have states of decreased CO2, which cause a left shift. All right. Okay, so when we think about increased or decreased metabolic activity, this is kind of a holistic way to look at all of the various factors that influence how hemoglobin wants to bind to oxygen. When we think about the Bohr effect, we're looking just at the effect of acidity on that relationship. When we think about the Carb-Amino effect, we're looking just at the effect of CO2 on that influence. But if we think more holistically, anything that increases metabolic activity also increases CO2 production, also increases temperature, also increases acid production, and those things will all shift our curve to the right, okay? So someone's asking, does the curve directly shift left or right, or does it also shift a little bit up and down? So it doesn't shift up or down. We can't bind more or less oxygen. We can only bind 1, 2, 3, 4. So it can go higher than 100. Remember, this is indicating our 100 mark, which is full saturation. But it can shift left or right, meaning the ease with which we can get those oxygens onto hemoglobin and the partial pressure that's required in order to do so. All right, so that's what's shifting and not necessarily the number of oxygens that are binding. That is pretty standard. Okay, but that's it.